All right, so the main idea to integration or antiderivatives is that you have to try to figure out where things came from. Okay, so if I were to give you a function f of x equal to 2x, and I were to tell you that that was the derivative of the function. So 2x was the derivative of some function. Then what would you tell me that the original function was if 2x is so x squared, right? So you would say f of x would be x squared. But could it also be x squared plus 5, or f of x be x squared minus 14? Are those also possible answers for being the original function, that the derivative of these right here? Let me write big F prime of x. All of these have the same derivative, right? So x squared becomes 2x, x squared plus 5 becomes 2x, x squared minus 14 becomes 2x. So how many possibilities could I write for big F of x? I mean, can I write like 100 different ways? Right, just change the number, right? And just give it a different constant, and I'll still have a 2x. So what we say is that the original function must have been an x squared plus some constant, right? We don't know what the value of c is. We could figure it out given enough information, but at least at first, we know that it has to be some kind of constant. It can't be a variable, because a variable would actually become a 1 or something like that. But if it's a constant, it goes away, so the derivative of big F of x would just become a 2x, right? So that's what we consider the antiderivative. In other words, we're working backwards now. Okay, where did these functions come from? So again, big F of x, let's put it right here, big F of x is called the antiderivative. Derivative. Now, usually we actually call it the integral, okay? So we'll say the integral of f of x. So you could call it antiderivative, you could call it the integral. You're going to notice I tend to call it the integral just because antiderivative it doesn't roll off the tongue as easy as integral. So I prefer just saying integral. But both of them can be used however you'd like. Okay, so there is a theorem that basically says that as long as you add the plus c to the function, you can encapsulate all the possibilities for the antiderivative. So what about something like this? If I were to give you a function like that, and I tell you what's the antiderivative of that, or the integral of 3x squared. Go ahead and say it. X cubed, right? Now, by the way, they're not all this, I want to say easy, but maybe you're thinking that's not that easy. But if you think about it, if you have x cubed and you take its derivative, you get 3x squared, right? But again, you could also write x cubed plus pi. You could also write x cubed minus, I don't know, 26. All of these have a derivative of 3x squared, right? So that means that the integral to lowercase f of x, so big F of x, would be x cubed plus c. Okay, that plus c is super important. A lot of people forget to write it down, and then you miss points on your tests. Okay, anytime you take an integral, and this is actually called an indefinite integral, but we'll talk about that in a bit. But anytime you take an integral of something, you need to put plus c if it's indefinite. And like I said, we'll talk about that definition in a bit. So, real quick, the letter C. This is called the constant of integration. Okay, so that letter C is called the constant of integration. If it has a name, it's important, so don't forget to write it down. Okay? Now, a normal function. Let's say, I'm just going to call it big G of x equal to, let's say, x cubed plus c, right now that we just wrote that down, right? I know I changed it to a big G of x, but big F of x, big H of x, whatever. They're all just integrals. And eventually you're going to notice we're not even going to use capital letters. We'll just use f of x and f prime of x to kind of say like, oh, look, this is the original function. F prime is what it became. If you're given a derivative, if you go backwards, just get rid of the prime symbol, right? So we're going to get rid of the uppercase letters soon. But that right there is called the general solution of the differential equation and we're going to call it g prime of x, which was 3x squared. So I'm just going to highlight the idea general solution. Whenever you guys see the words, and you're going to see this maybe even in the AP exam, they'll say find the general solution. Sometimes they say find the particular solution. Now, general solution means it's going to have a plus c. Particular solution means that you're actually going to have to solve for what the value of c is. You're going to have to figure out what exactly is c. Maybe it's a plus 14. Maybe it's a minus 3. You're going to have to solve for that. So general solution means that it's going to have a plus c at the end. Particular solution means that you're going to actually figure out what c is. And we'll get to those eventually as well. Okay? So make sure you guys kind of have those two things figured out right there. Okay, so general solution, in other words, it includes the plus c's after you integrate. Okay, now what are differential equations? Well, we actually talked about those before. So differential equations, just to give you some example, are things that we've already done, like y prime equals to 2x, or if you want to write it like dy dx equal to 2x, or remember we sometimes wrote it 2x dx, right? That was from section 3.8. So those are differential equations. In other words, an equation you took a derivative of, you differentiated, so they call them differential equations. Okay, the y prime, remember, that's just a shortcut to writing f prime of x, right? You could also say like f prime of x equals to 2x, right? That's another way that we wrote derivatives. So any one of those can be considered a differential equation. So whenever you take the integral of one of those differential equations, then we call it the general solution. Okay, when you figure out where it came from. So just one more time here. What if I told you, let me put like example number 1 here. Find the general solution of y prime equal to 4x cubed. Just take a take a quick minute. Try to see if you can figure out what the general solution is. So what'd you guys come up with here? What's, I guess you could say, what's y? There you go, x to the fourth plus c. All right, so that's your general solution. If you were to take a derivative of that, then you would have 4x cubed. Right? Because the derivative of c, which is just a constant, the derivative of a constant is 0. Right? So that's why we don't have to write it. So there you go. So let's talk about the notation. What does this look like normally? So notation for antiderivatives. Or you could say integration. Again, I say integration. Sometimes the book will say antiderivatives. Interchangeable, it's up to you. So this is what it looks like. You normally start off with a function dy dx equal to f prime of x. So we're just going to kind of build it. Okay? Actually, we should just call it f of x, should be fine. Just call it f of x. Now, what I'm going to do is I'm going to transfer the dx over. So dy equals f of x dx. Now, to solve for y, because again, dy is our derivative, I want to find out what was the original function. So this is what I do. I'm going to write y equals to the integral of f of x dx. So that big symbol is the integral. And that's equal to big F of x plus c. Now let me label a couple things here. So first off, this is your integration symbol. So that's how you tell people you're integrating. This piece here is called your integrand. In other words, this is what you're integrating. The dx, that's called your variable of integration. So that's the variable of integration. And remember that plus c is your constant of integration. Okay, so those are just the parts. Now we're going to talk about how we do this. But before we do that, just to give you a couple of basic rules, and then we'll go over the main idea. But when you read this, okay, so when you guys look at that and you're going to read it, you're going to read it like this. So this is read, okay, the integral of f of x with respect to x. Okay, so we read it, the integral of f of x with respect to x. Now, there are two ways that you can see integrals. Usually, you'll see integrals like this. Y equal to the integral from a to b of f of x dx. Or you might see it like this. Y equals to the integral of f of x dx. Now, we're working on the right side one, okay? But just so you know, this right here is called a definite integral. And the reason why is because they give you the interval from a to b. In other words, they want you to integrate from a specific interval from a to b. And we'll learn more about that tomorrow when we actually, or not tomorrow, but when we do section 4.2, because that's when we're going to figure out how integration is basically area. So they got to give you a certain interval to figure out the area beneath curves. But that's what we use definite integrals for. The other side, these are called indefinite integrals. Because they don't give us an interval. So it's not defined, right? So if the interval is defined, we call it a definite integral. If it's not defined, we say it's indefinite. Okay, so whenever you hear those terms, if they say definite, that means they have to give you intervals you're going to integrate with. If they call it an indefinite, then that means there's no need to put upper and lower bounds, okay, the a and b part. All right, so some of the basic rules before we actually get to the how to integrate, instead of just guessing, because so far that's what we were kind of doing, right? Kind of looking at it and saying like, okay, where did this come from? Let me think, maybe if I do this and that, I can get that function. So some basic rules. So basic rules for integration. So there's two of them, and then there's two big ones, and then there's a bunch of little small ones. So we're going to talk about those. Okay, so number one, the first one is that the integral of big F prime of x dx is equal to big F of x plus c. In other words, what they're trying to show you is if you integrate a derivative, you get back the original function. That's what they're basically saying. So notice how they were integrating big F prime of x. So the integral gets rid of the derivative. You guys see that? Like it undoes the derivative. Okay? And then there's another part that says if the integral of f of x dx is equal to big F of x plus c, then the derivative of that integral is just the function on the inside. In other words, some people say, oh, so the derivative cancels the integral. In a way, yeah, because remember, integration undoes derivatives, and derivatives will undo integration. Okay? I guess you could say it's like they're kryptonite, right? Each other, that they would basically undo each other. So if you take the derivative of an integral, you get back the original function that's inside. Okay, so notice your answer is right there. Okay, now just a couple little things that you guys have to kind of remember. Okay, so I'm going to kind of make a list on two sides. So there's differentiation, and then there's integration. So these are still some of those rules, okay? So when you took a derivative of a constant, we got 0 for derivatives, right? The derivative of a constant is 0. For integration, the integral of 0 results in a constant. Okay, for derivatives, if you took a derivative of kx with respect to x, your answer would just be k. Right? That's what we did in derivatives. Like, so if you have a derivative of 2x, you just wrote 2. Right? With integration, the integral of kx, the integral of k dx, so notice k is a constant, okay? Whereas the one above it was 0 becomes a constant. For the next one, it's an actual number. So the integral of 2 dx, the integral of negative 5 dx, okay? Not just 0, but an actual number that's not 0. Then you get kx plus c. So in other words, the integral of 2 dx would be 2x plus c. The integral of negative 7 dx would be negative 7x plus c. So we're adding the variable back instead of taking it away. With derivatives, if you had k f of x, then you would ignore the k and then take the derivative of your function, right? And then just multiply it together. That's what we did with derivatives. With integrals, if they give us a k f of x dx, what they say is bring out the constant and just integrate the function. So it's kind of the same like with derivatives, right? With derivatives, we just used to say, oh, if you have a constant in front of a function, ignore it for now, take your derivative of your function and then put it back later. With integration, they say the same thing. They say, well, if you have a constant in front of a function, just ignore it, bring it out. Don't integrate that, but then integrate the function itself. And if you're thinking, well, wait a minute, why did we integrate the constant on the second one, but not on the third one? Well, because on the second one, it was just a number. That's all we were integrating, was just a number, like a 2. But if you have a whole function next to that 2, then they say, oh, in that case, ignore it, move the 2 out, and then integrate the function itself. Okay? So you can integrate a constant times a function, just ignore the constant at first, and then integrate the function. With derivatives, you guys had the ability to take derivatives of things that were added or subtracted, right? You would just do like d dx of f of x plus or minus d dx of g of x. That's the way we worked with derivatives. If you had two functions adding or subtracting, you would do each one individually, right? And then you added or subtracted whatever the function was inside. You have the same capability with integrals. So if you have something like this, okay, so if you're adding or subtracting two functions in an integral, you are allowed to break it apart into two different integrals. Notice how the dx follows to both of them, okay? That dx is kind of like a period to a sentence. So I always tell people, think of this part right here as your capital letter, and this is your period. You can't not have those, all right? Or else it's incomplete. You have to have the integral symbol and the respect to whatever variable symbol, okay? You have to have them both. You can't ignore them, or else your sentence is not complete. It's like taking your AP English exam and writing sentences without capitalizing and without using periods. They're going to say, well, great, you wrote a lot of stuff, but where are your complete sentences, right? It's not good. So it's the same idea with integration. You got to have your integral symbol. You got to have your respect to symbol. So dx, dy, dt, whatever it happens to be, you got to have it there. Okay? But notice, just like with derivatives, you can split up the functions. All right? Now, we don't have a product rule, and we do not have a quotient rule for integrals. Okay? They don't exist. So the only other rule that we learned with derivatives was the power rule, which was actually the one of the most important rules. Right? And what you did was you took the n down, and then you multiplied by the function itself, and then you subtracted by 1 on the power. Now, that is, I told you guys, probably one of the most important rules for derivatives, and it's the same in terms of integration. It's one of the most important rules of integration. So if you have the integral of x to the n dx, your answer for this would be x to the n plus 1 divided by n plus 1 plus c. So notice how with derivatives, you multiplied by your power and you subtracted 1. So you multiplied and subtracted. Notice how with integration, you add to the power, so you do the opposite. And instead of multiplying by the power, you divide by the new power. So they're doing the opposite things, right? Because like I told you, integration undoes what derivatives do. So if a derivative multiplies by n, the integral will divide by the power, and that power is a plus 1 now, right? It's adding instead of subtracting. But this is called the general power rule for integration. Okay, so one real quick thing though, there's a really important thing here. N cannot equal to negative 1, because if n is equal to negative 1, then what happens to my denominator? It becomes a 0, and we can't divide by 0, right? So there is actually a specific thing that we do when n is equal to negative 1, but for now we're not going to do that. Okay, so super important. Okay, I'm just going to kind of box this thing. This is one of the most important things you're going to have to know for integration. Okay, that power rule. That's going to get you through most of the problems. Okay, the problems you can't do, we talk about in section 4.4, I think, when we talk about substitution. Okay, but for now, that's one of the most important things. Now, we are going to do the rest of these, and these you're going to say, oh my gosh, these exist here. Yes, they do. D dx of sine of x was equal to cosine of x. Okay, so that means that the integral of cosine of x dx is what? What should I expect it to be? So that's going to be sine of x. Okay, the derivative of cosine of x is negative sine of x. Now this one's a little trickier. So the integral of sine of x dx is what? Say that louder. Negative cosine of x. Right? The reason why it's negative is because notice the derivative had a negative on the integral. I didn't mention it, therefore it comes out on its integral. Yes, these are things you guys should memorize. Okay, all these trig functions for derivatives and for integral, you have to know them. D dx of tangent of x is, you guys remember the derivative tangent? Secant squared x. So that means that the integral of secant squared x dx would be tangent of x plus c. D dx of secant of x. Well, that was secant x tangent x. So that means that the integral of secant x tangent x dx is secant of x plus c. By the way, I think after we're done with these definitions, we're going to stop. And then tomorrow we'll do a lot of examples. Yeah, and we might actually take 3 days on this. I'm not sure. But once we get through all these basic rules, that's when we stop. So maybe we'll do a couple examples, but we'll see. Some easier ones. So d dx of cotangent of x. Well, that's negative cosecant squared x. So the integral of cosecant squared x dx would be negative cotangent of x plus c. And there's one more. Last one. Last trig function. So d dx of cosecant of x. That was negative cosecant x cotangent x. Again, all these definitions on the left come from chapter 3 and chapter 2, actually, to be more exact, chapter 2. So that means that the integral of cosecant of x cotangent of x dx is equal to negative cosecant of x plus c. Just curious here. Yeah, we got time. Let's do 3 quick examples, just so you guys can kind of practice this a little bit and see if this kind of helps you out. And tomorrow we'll work on some more. But let's do a couple of these. All right, so example number 2. So we're going to find the integral of 12x dx. Now I'm going to do this according to the rules that they told me, okay? Eventually you can do this a lot faster, but at first sometimes it takes a little bit of time to get used to it. So if they want me to do the integral of 12x dx, notice this is the kx situation, right? K times a function x. Okay, so I'm going to get the 12 and then write x dx. Now I do want to remind myself that the power on that x is a 1. So I'm going to use the power rule on the integral of x to the first. In other words, that's like x to the n, right? So this is going to be 12 times. So according to the power rule, I'll write it up here. X to the n dx will be x to the n plus 1 over n plus 1 plus c. Okay, that's the power rule. So that power, x to the first, is going to become x to the 1 plus 1 divided by the new power, 1 plus 1, then plus c. Okay, so I got the original power, I added 1 to it, and then whatever that power happens to be, I divide by it. So 1 plus 1, that's what I'm dividing by. So this is 12 x squared over 2 plus c. Now I'm going to distribute that 12. So 12 times x squared over 2 becomes 6x squared plus c. Now, if you're wondering where did the 12 go, well, what's 12 times a constant? So any number. So what's a number times a number? It's a number, so I'm just going to put plus c. It's 12c, but 12 times a constant is still a constant. Okay? So there's your answer to that example. Now, if you take the derivative of that, what do you get? 12x, right? Plus 0. So that's how you can check, did I do it right? Take a derivative. Right? So, all right, let's try another one. Example number 3. We're going to find the integral of 1 over x squared dx. Now you might say, wait a minute, you didn't teach us anything with fractions. Well, I told you that there's no power rules. That means, no product rules and no quotient rules. That there's no product or no quotient rules. So that means you have to rewrite this. So you don't want it to be a fraction. You want to rewrite it so it's just the power rule. So x to the negative 2. So again, I'm just going to use the power rule. I'm going to add 1 to the power and divide it by the new power. So this is what it's going to look like. X to the negative 2 plus 1 over negative 2 plus 1 plus c. Now negative 2 plus 1, that's a negative 1. So that's x, let me write this a little lower here. X to the negative 1 over negative 1 plus c. Well, x to the negative 1 is the same as 1 over x. So I'm just going to write negative 1 over x plus c. And that's my answer. Remember, the negative 1 in the denominator just became a negative in the front. That x to the negative 1, I rewrote it as a fraction, 1 over x. And again, if you want to check to see if you got it right, take a derivative of that function, and you should get 1 over x squared. Let's just do one more. Like I said, just to kind of get your feet wet here. Example number 4. So we're going to find the integral of the cubed root of x squared dx. Now, if I were to ask you to take a derivative of this, you might say, well, maybe I have to do a chain rule and stuff like that. There are no chain rules in integrals. Okay, so that might make you feel even better about it. No chain rules, no product rules, no quotient rules. Okay, there are tricks that you can learn, which you learn in BC. There's only one trick that you learn in AB, which is basically the substitution, which is in 4.4 and 4.5. But other than that, there are no other types of like special rules. So in this case, what you're going to have to do is rewrite it. So you're going to integrate x to the 2/3 dx. Because remember, the cubed root of x squared is the same as writing x squared to the 1/3 power, which is the same as writing x to the 2/3. So that's how I got x to the 2/3. Now, I'm going to go ahead and integrate that by using a power rule. So I'm going to do x to the 2/3 plus 1 over 2/3 plus 1 plus c. So 2/3 plus 1, that's 5/3 over 5/3 plus c. But don't leave it like that. At least fix the denominator. Since you're dividing by 5/3, it's the same as multiplying by 3/5, right? You multiply by the reciprocal. So it's 3x to the 5/3 over 5 plus c. And remember, you can take a derivative of this to make sure that you actually get x to the 2/3. Any questions on any of these three? Notice we only use one main rule, basically was the power rule. Okay, that's all we're doing. So let me go ahead and stop it here. And again, tomorrow we'll continue.